In Chapter 10, our final chapter, I will show you just a few what I might call advanced techniques that are used in shell scripting. They tend not to fall into any other categories, so I've just bundled them together and put them into one chapter here. Let's have a look at them one by one. The first is what I might call debugging. All the programmers that are listening to this will probably be aware of the meaning of the word debugging. For the rest of you, it simply means fixing up unexpected errors in your program, i.e. bugs. So sometimes your script will not work properly. Now when that happens, it is sometimes obvious why it's misbehaving. It might be doing something very obvious and you go, oh yes, that's such and such, I know how to fix that. But then sometimes it's not obvious. And it's at that point that you need to invoke the shell's special built-in debugging facility. It's very simple. There's not a whole lot to it, but it does usually help you fix the problem. It involves script with the -x option. The -x option is actually an option to the shell. So you would have to run your shell script like sh-x and then the name of the script, as you can see on the screen. Now what that does is just before each command is about to be run, the shell echoes out to the screen exactly what it's about to run. And the important point about that is that all special characters such as wildcards, variable substitutions and so on have already been substituted or processed by the shell. So you'll be able to see what variables are actually set to and what wildcards actually expand to and so on. So the simplest thing to do is to probably have a look at this. Here's our contact script that we actually completed at the end of Chapter 9, and I've introduced a little bug into it. And I'm not going to tell you where the bug is, I'm just going to run the script and see what happens. So we'll run it now, and the file is test.dat, and it's in the create record section, so let's have a look at that. I'll just enter some rubbish. Are these details correct? Yes. Okay, so we've got an error message. /contacts, file name, ambiguous redirect. Okay, now what does that mean? It's a bit difficult to tell. Now we could look at the code, so let's do that. So I'll quit out of this and quit, yes, and we'll go down to the actual code where that is created, which I believe is somewhere around here. And there it is. That's the line where it's coming out. I know that because I just put it there. Now even knowing that much is probably more than we would know some of the time, but I do happen to know that that's the line where the mistake is, but I can't see the obvious mistake. So what I'm going to do is I'm going to run the script again, and this time I'm going to use the -x option. Now it is going to make the output look very, very messy, because interspersed with all the output that we want to see will be all the debug output, which is every command getting executed. But that's what we do when we debug, so let's have a look. So it's sh-x and then this script and then the parameters to this script, which is test.dat. Now you can see that all the lines that begin with a plus are what the shell is about to do. So for example, one of those echoes, echo \t 1: create records, so that's echoing a tab character followed by a 1 and then create records, and then you can see that the very next line is what actually happens when you run that particular statement. So it's just a bunch of echoing at the moment, so let's actually choose one of those. We'll choose number 1 because that's where the problem lies. And notice that the very last thing that it's just done is a plus read name. So that's the very last statement that got executed, so it's now waiting for us to type something. So I'll just do all the typing that I did before, and we scroll through each one of those one by one. Okay, so are all these details correct? And I answer yes, because I want the bug to occur. And now somewhere in there is the error, so let's have a look at it. We've got the return 0, then we've got the echo, all that nonsense that I typed in, and then we've got the error message. Now that echo statement actually looks okay, but you will recall, and I'll just quit out of this, that there's supposed to be a greater than file name on the end. and that's supposed to come up on the debug screen, which tends to indicate to me that there's some sort of problem with the actual file name variable itself. So what I'll do is I'll just put a little bit of test information in here. So I've just added, I want to see what the value of file name is at that point, because there might be some problem there. And I'll run all that again, and we choose option 1, enter some details, and the answer to this question is yes. Now, notice that right here is that echo of the file name, but the actual file name has been substituted, the variable has been substituted, and we don't see anything at all. So somehow that variable is not set to anything, which is a pretty good reason why we wouldn't be able to echo this output into that file name if the file name was actually blank. So here we are back in the code, so that echo statement has served its purpose. So what I would probably do at this point is scroll down to the point where I believe that I've actually set the variable called file name and find why it's not being set. So I scroll down and down and down, and here we are. So that's the point where I'm setting the variable, or where I believe I'm setting the variable, and here is the problem. The variable is actually called fname, not file name. So I've made a little mistake with my naming of my variable. So I can go back to where I was and change that to just fname by itself. And, well, that's going to fix the problem. I know it is, because I put the bug in there in the first place. So you'll just have to take my word for it. The program has now been fixed. But the point is, it was made easier for us to find the bug in the first place by using the sh-x. We probably could have found it anyway if we'd spent a bit more time, but the sh-x option certainly does help. I'll show you the most common sort of error that you typically stumble across and where sh-x will help you. Here's a simple script. We've probably seen this sort of code 100 times. Please enter your username, read it, then test to see if that's equal to root, and then if it is, echo out you're the super user, otherwise you're just a regular user. Okay, so let's run this script now. And please enter your username. Now I don't enter a username, I just press enter, and I get sample, bracket, colon, equals, bracket, unary operator expected, and what does that mean? Who knows? Maybe if I'm not new to shell programming, I'd go, well, that's a weird kind of error. So instead, I would do this. I would do sh-x%. Please enter your username, and again I press enter. And the line where I actually do the testing to see if it equals root, that begins with a plus. As you can see, we've got plus, then the square brackets, and then equals root, which immediately makes me think, hang on, there's supposed to be something on the left-hand side of the equal sign. So I go back into the program and think, yes, well, there is something on the left-hand side of the equal sign. How come that didn't get displayed? And the reason is because we just press enter. We didn't set name to anything. So, what's the solution? Well, you might recall that the way to actually make there be something there, even if name is empty, is to do that. And I'll run it again. And please enter your username, press enter. And this time, you can see that just there's actually, this time, there is something on the left-hand side of the equal sign. It's the empty string, but there is something, and so the test program does not have a problem with that. And we don't have any more problems with the shell script, so we could just run it in the normal way this time, and please enter your username, and you are a regular user. Now we don't get any error messages, and everything looks fine. Okay, so that should give you an example of how you can use sh-x for your debugging needs. This module describes a simple shortcut that you can use for setting default values for variables. Now, you often find yourself writing code that looks like the following. Test to see if a variable is set. In this case, test to see if var1 is set. Or in this case, test to see if it's not set. And if it's not set, then set it to its default value. We frequently need to do that. Now, there is actually a shortcut for all of those 4 lines, and it is just the following. The syntax is a little confusing, so bear with me. We've essentially got our $, followed by some information enclosed in curly brackets, in braces. And it's almost like inside the curly brackets we're just saying var1 equals whatever its default value is, but it's not exactly that because we've put a colon there as well. It's var1 colon equals its default value. So if you can get your head around that and remember it, it's actually a very useful thing rather than typing the above lines. There's only one little problem with that, and that is if you just type that line in on the command line by itself, it will in fact set var1 to be, in this case, some default value, but then the shell will actually try and run that as a command, which is not what you want. So instead what you typically do is you put a colon, which is a command that does absolutely nothing, and then you specify all of the above as the first parameter to the colon. In other words, you're specifying it as the first parameter to a program that does absolutely nothing. So the program, the command line, will do nothing, but the variable will still get set to its default value. Alternatively, you could say simply assign that to a second variable, which would cause var1 and var2 to both be equal to the same thing. So let's have a look at that now in a script. Here is a little test var script. Now I'll run this and see what we get. Now we get an error message saying hello, command not found, and var1 is set to hello. So var1 actually does successfully get set to hello, but as you can see, the very first line there is treated as a command line in its own right. In other words, the variable is substituted and it evaluates to hello, so hello is tried to be evaluated as a command line. We don't want that, so we insert the colon like that, and we try it again, and this time we don't get the error message, but var1 is still set to hello. So what happens if var1 is already set to something? Okay, so I've just inserted a line that says var1 equals initial value. So theoretically, this line here should do now absolutely nothing because it won't set var1 because var1's already been set. So let's test that. And var1 is set to initial value. So the second line, the one that the cursor's currently highlighting, is in this case a line that does absolutely nothing at all because var1 has already got a value when it gets to that point. So there's a nice little trick that you can use. It's a handy default setting and a useful shortcut for. You're probably not aware at this point, but there is a problem that comes up when you try and deal with temporary files. Now it's not an immediately obvious problem, but let's have a look at it. Now let's just put the following very simple line into a shell script. Take any old program, in this case who, and send the results to a file called who results in the temp directory. Now what's wrong with doing that? You're not going to get an error message on that command line. That command line is going to run perfectly well, but there is an inherent problem with using this particular technique. And what you might want to do is pause and have a think about it. Pause the video at this point, have a bit of a think about it. And I'll give you a hint if you're having trouble. And what if this was a very commonly used script? That's your hint. So perhaps again, pause the video and have a bit more of a think about that. Okay, did you come up with an answer? Well, here's the problem. There actually may be many people running the script at the same time, in which case they'd all be running the same line of code, which means that several people would be trying to write their details, whatever those details happen to be, to a file in the temp directory called who results. And somebody else might be deleting the file because the shell script may go on and delete the file a bit later on, so someone may be deleting the file while the other person has just written to it, and well, all sorts of errors can come up. As you can see, we might have several people all trying to deal with the same data and all thinking that it's different data. So what's the answer to this? How can we actually come up with a name for our temporary file that is guaranteed to be unique to this instance of the script that's running? This is a tricky one. I don't expect you to know the answer, but you might like to have a bit of a think about it. Is there a name you could possibly use that would be different every time the script is run? So perhaps again, pause the video and have a bit of a think about that. Alright, let's have a look at the answer. The secret is to use the $$ variable. And $$ is another one of those clever little variables that we've got at our disposal, like $?, and $hash, and $, and so forth. This contains the process ID of the current shell, which in fact in this case would be the shell that's running the script. So, if you think about it, that completely solves the problem, because you can use $$ as the name of the temporary file, or at least part of the name of the temporary file. You can append a bit of text on the end of the $, or put a bit before it if you like as well. So it might look something like this. It's very common to use the actual name of the script as part of the temporary file name, just so that you know where the temporary file came from, and then maybe put a $$ on the end. So you might have the actual file name might end up being myscript.12345, and when the next person runs it, it would be myscript.12346, and so on. And if you think about it, that does indeed completely solve the problem, because there's no way that the same process could be running the script twice simultaneously. So that's pretty much all I want to say about that. You can run that up in a little test script yourself if you want and test it, but it's very simple. It's just a matter of knowing the secret, and you know it now. So I've called this module Preventing Abnormal Termination. Now let me explain what I mean by that. Most of you will probably be aware that it is possible to kill a process. In other words, you just use the kill program and specify the process ID, and what happens is the program dies. Well, it usually dies. It doesn't always die, and I guess in this module I'll be explaining why it doesn't always die. I'll actually give you the knowledge to design your program in such a way that you can do anything you want if someone tries to kill you. First, we have to understand what actually it is to kill a process, what it means. Well, what actually happens is when a process is killed, that process is simply sent a signal. A signal is also often known as a software interrupt. And then what happens is, if that process is not designed to handle that signal, and most processes are not designed to handle signals, then that process simply terminates. But it is, as I just mentioned, possible to handle any signal if you simply know how, and that's what I'm going to show you in this module. So any program, which of course includes any shell script, can be designed to handle signals and do meaningful things with them. So why might you want to handle a signal? Well, I can think of three possible reasons for wanting to handle a signal. The first is to prevent the program from terminating. In other words, you may not want to terminate the program upon receipt of a particular signal. It may be vitally important that your program keep running, and so you would of course want to make sure that all signals that could possibly be sent to your program are essentially ignored. Secondly, you may actually be quite comfortable with the program terminating, but you don't simply want to abort the program. You may have a collection of temporary files that are open and being used. You may have even connected to a database or something and need to disconnect from that using a particular command. In other words, just restoring the system to a known good state. So what you would do then is, when you receive the signal, you would initiate the process of cleaning up all your temporary files, logging off the database, or doing whatever it is that you need to do to get the system back into a good state, and then deliberately and purposefully exiting yourself. And the third reason is, you may actually just want to perform some custom action upon the receipt of a particular signal. There are many signals that a process can receive, many different types of signals. And you may actually want to take advantage of that and say, okay, whenever I receive this signal, it means I'm supposed to do this particular action. Which means, of course, that you can then use signals as a form of inter-process communication. Which means you might have a shell script that's running, it might have been running for a while, and you wanted to do a particular action. And so you can do that from any terminal on the system. You can simply send that particular shell script a signal, a particular signal, and that shell script will perform the custom action that has been designed to do when it receives that signal. So essentially you can communicate with that running shell script from anywhere, which is very handy to be able to do that when you think about it. So I need to mention all the different types of signals that are available. I'm not going to go through all of them because there's a great deal of them, and they actually vary from one Unix to the next. There's typically over 20 of them, and most of them you'll never see ever in the course of your programming life. But there are a few that do occur reasonably often, and I'll tell you what they are and when they typically come up. The first is signal number 1, which is what we call the SIG-HUP signal, which HUP is short for hang up, and that occurs whenever the user's terminal is disconnected or the login shell is terminated. And that can happen when the modem hangs up that you're connected to, or a telnet session's interrupted, or a network goes down, or your terminal becomes unplugged, or whatever. So what happens then is that every process that's running in your process group, in other words, every process that has been started by your login shell, will receive a hang-up signal. And what they will typically do is simply exit. It's like, well, the terminal's been disconnected, so there's really no point in keeping this program running, so they exit. The second signal is signal number 2, SIG-INT, and the INT is short for interrupt, which occurs whenever the user presses the interrupt key on the keyboard. And the interrupt key is usually set to Control-C, although it can be set to anything that you desire. Now we like to take advantage of that. If we've got a program that we've just started on the command line and we decide that we need to abort it, then we can just type in Control-C and it usually just exits and goes away. But a program, of course, can be designed to not do that, to not exit when you press Control-C. And I'll show you how to do that in a moment. The third signal is signal number 3, called SIG-QUIT, and it's just like the interrupt key. There's actually another key on the keyboard that does a very similar thing. It's the Control \key. So those are 3 of the most common ones. There's also another extremely common one, which is signal 15, the SIG-TERM. Now that actually happens when Unix shuts down. When Unix shuts down, it actually sends a signal 15 to every single process that's running on the system. And that is their little notification that the system is shutting down. And what they will typically do is just exit at that point, either by handling the signal and choosing to exit, or just by not handling the signal and being killed anyway. Or if you type in kill and then the process ID on a command line, using the actual kill program, it does actually send signal number 15. So those are the common ones, and those are when they occur. There's actually a couple more, SIG user 1 and SIG user 2, which have been specifically set aside for programmers to use to enable inter-process communication, just like I talked about before, to perform some custom action. Now these tend to vary from Unix to Unix, and on the Linux system that I'm using they are SIG user 1 and SIG user 2 are 10 and 12 respectively. Now just a couple of things to keep in mind. Firstly, it's actually possible to send any signal to a process using the kill program. For example, I could send signal 10 to process 12345 just by doing a kill -10. So you can actually simulate various sorts of system events. For example, you could simulate your terminal being disconnected by sending a kill -1 to the particular process that you were involved with. And the second thing you need to notice is that it's actually not possible for any process, any shell script or any other program, to handle SIG-9, which is what we call the kill signal. So if you send a -9 signal to any process, kill -9, then that process is almost guaranteed to die. I say guaranteed because there's absolutely no way that it can say, no, I choose not to die upon receipt of signal 9. So now we get to the point where I actually tell you how to handle these signals. And here it is. We use the trap command, which is it's an actual shell built-in command. You typically put it at the beginning of the script rather than halfway through or anything like that, because the handling of the signal will not take effect until the trap command has been run. And it looks like this. You specify as the first parameter the command that should be run upon receipt of the signal that you specify. And then you specify the signal or signals. You can actually specify several signals on the one trap command line, and the same command that you specify will be run upon receipt of any of those signals. So let's have a look at what I'm talking about. I'll give you an example of that. This is something a bit silly, but it's actually very simple. we're going to run the ls program upon receipt of either signal 1 or signal 2. So that's pretty much all there is to it. You put that line at the beginning of the script, and any time a signal 1 or signal 2 arrives at the script, the ls program will be simply run, and then the script will resume its processing that it was doing. So it could be in the middle of doing something else, it could be in the middle of a read, it could be in the middle of anything, and it will run the ls program. And then it will resume whatever it was doing. It will move on to the next line in the script, wherever it was just at when the signal arrived. If you actually want to ignore the signals, then you just use double quotes just by themselves. In other words, the empty command or the empty string becomes your command. So it would be trap and then a pair of double quotes by themselves and then the signal numbers. The command that you specify can even be the name of a function, and it's also possible to specify parameters to either that function or any other command that you want to run when you receive the signal. And here's an example of that. We might have a little function called graceful exit, which could clean up all the temp files, log off the database, or do whatever it is that you need to do, and then exit. So the last line on the example that you can see in front of you is that whenever I receive a signal 1, 2, or 15, I actually want to call graceful exit with a parameter of 2. And that 2 is going to be used by graceful exit as its exit status. So if you need to actually provide parameters to your command, you actually have to put the whole command inside double quotes. So I'll show you an example of all this in action. Here is a script I've called testsig, and as you can see it just echoes a bunch of lines out to the screen and then sleeps for 1 second between each one. That should hopefully give me about 10 seconds to get a kill in process when I actually start the script. And if I receive a signal 1 or a signal 2, then I run an ls-c. So what I'd like to see happen is this is line 1 appear on the screen, then a second later this is line 2, then a second later this is line 3, and while they're all happening there, I'm going to be trying to kill the process. So I'll take a note of the process ID and then I'll kill it with the signal 1 or 2, at which point the ls should get output to the screen, and then it should just simply continue on with the next echo that it was going to do anyway. That will hopefully prove to you that processing resumes where it left off when the signal arrived. So let's test it and see if it works. I'll quit out. Now what I'm going to do is I'm going to run testsig asynchronously on the command line, so I've got a chance to type in a kill, and I'll have a grand total of 10 seconds to find the process ID, type it in, and see if it works. So let's do that now. Okay, the process ID is 10607, and there is the output of the ls, and as you can see this is line 7, this is line 8, this is line 9, this is line 10, also appear immediately afterwards. So if you follow it down you can see this is line 1, this is line 2, it all gets a bit mixed up there because I'm trying to type at the same time, and that typing comes out on the screen as well. This is line 3, 4, 5, 6, and then somewhere in between 6 and 7 I actually get the output of the ls program, chap 1, chap 2, chap 5, chap 7, chap 9, and so on. And then I get, of course, the rest of the echo, 7, 8, 9, and 10. So I hope that proves that it's working, and that's all I really need to say about trapping. Let's now do the final course exercises for this. Okay, so here are the final chapter exercises for the course. The first exercise is create a little script that does nothing at all except sit there and sleep. And when I say sleep, I mean really just do nothing at all except sleep. And whenever a SIG user 1 is received, I want the program to display the current date and time followed by the current calendar month, and then continue doing nothing at all. So the whole purpose of the script will be to sit there running off in the background in a corner somewhere, and whenever we send it a SIG user 1 signal, it will display for us the current date and time and the current calendar month, and that's the sole purpose of the script. Now, because SIG user 1 varies from one Unix to the next, you'll actually have to find out which signal SIG user 1 is, and you can use a kill-L to do that. That just lists all the signals available to you. And if you don't have a kill-L option available on your Unix, then just simply use the signal number 2. The second exercise has relating, of course, to the course project. I want us to finally complete the project putting in the search and delete options. The search option should actually prompt the user for a pattern to search for, and then display all the records that contain that pattern, all of the records, in the standard list format that we're already using to display the records that we have in the database. And the delete option should also do exactly the same thing. It should prompt the user for a pattern to search for, and then if it finds any records, it should ask the user if they want to delete all of those records. And if they say yes, it should, well, obviously delete the records. Now, at some point, I'm guessing that you'll need to use a temporary file in the delete option. So remember what I said about temporary files using the $$ facility there. Also, if either sighup or sigterm are received, then I want the program to exit immediately. And if sigint or sigquit are received, then ask the user our question about whether they want to quit. Do you really wish to quit now, or whatever. And of course, if they answer yes, then you should quit, and if they don't answer yes, then you should simply continue whatever you were doing. Now, what I'd really like to see in your finished product, well, I guess I never will see it, but you'll see it, is try to avoid repeated code. In other words, if you find a piece of code that you need that does exactly the same as some existing piece of code, rather than copying and pasting that piece of code into two separate places in your program, turn the code that you need more than once into a separate function by itself, and then just simply call that function from each point in the code. That makes programs infinitely more reusable. Okay, well, good luck with that, and I'll see you in the next one. And here are the solutions to the final exercises for the course. Here's my solution to the signal question that I posed to you. I have a program whose sole purpose in life is to just go around this while loop, just sleeping for 1 second each time through the loop. And then, at some point, if a signal 10 is received, then we can call the function called processSig, which is this process up here, which simply does a date followed by a cal, and I've put a little blank line there just using echo, just to make the output neater, and you'll see why in a moment. So let's run it and see if it works. Sig test, run it in the background, and it can just go off in the background and do nothing all by itself. And I know that its process ID is 10896, so I'll kill that with a -10 signal, 10896, and see what happens. And there is the date and the calendar. And I can do that again, kill -10, 10896, and there's my date and calendar again. And that will continue indefinitely until I get bored. Okay, now if I really want to kill the program and actually make it stop, I can kill it with some other signal. Just kill it by itself. That will send it a 15 signal, a sigterm, and then, as you can see, that terminates the process. Okay, so that was working quite well. Now let's have a look at the course project. Okay, there were quite a few changes made to the project this time around, so let's go through them one by one. We need a temp file, and I've just decided I'm going to put that up the top. I don't have to put it up the top, but it's nice to do that just in case. The user might decide that the temp files should not go into the temp directory, they should go somewhere else, and so they can easily change that by changing this line right at the top of the file. And what else? Pause is the same, yes, no is the same, usage is the same. I now have a function called quit, which looks like this. And it says, do you really wish to quit now? And if they say yes, then I exit using the single parameter to the quit function. So the quit function actually takes one parameter, which is the exit code, to use with exit here. Now I actually have to store that away in a variable, because if I call one function from another function, then $1 gets overwritten. You can test that out for yourself if you like. Anyway, so I'm going to call quit. Quit is going to be my standard way to get out of the program. We'll obviously call quit whenever we receive a signal 2 or 3, and we'll also call the quit program whenever the user selects the quit menu option. So let's move on. Now I actually created a little function called heading because I didn't want to actually have to put out this code twice, and it's just those two lines of code there, just a couple of echoes. The reason I put them in a separate function is because otherwise I would have had to duplicate those lines of code. And again, I've got another function here which I've created simply so I don't have to duplicate code, and that is how to print out the actual records from the database. We're going to need to display them using the search option, and we're also going to need to display them in the view option. So rather than have those lines of code twice, I thought I'd put them in a separate function all by themselves, and this is what it looks like. It's a rather clever function. It reads information from standard input, this function, so you can actually pipe, using this example here, you can actually, for example, pipe information to this function from grep or from cat or from anywhere else. And what it will do is it will sort them, sort the standard input, sort the lines of input that it receives, and that's the sort option that we used before, sorting via the second field. That's what the +1 means, sort via the second field, and the -t colon means that fields are separated by colons. And for each line we'll just simply display that in the awk way, and that's just cut and pasted from the awk line that we had before. And that's pretty much all that the print records function does. So print records and the one just above it, heading, are going to be used whenever we need to print out information about the records in our database. And now create hasn't really changed at all. View will have changed because really now I just call heading, and then I cat the file name and just pipe the results to print records, which, as we saw a moment ago, will sort the output and essentially pipe it to awk. And then all of that is collectively piped to the more program, so we see it one page at a time. So that's the view program. Obviously we also display how many there are. Now here's the new search program. We ask them to enter a pattern to search for, and I've also allowed them to actually not enter any pattern at all. They can just press enter at this point and they'll see all the records. Now I just use grep to see if there are any, and I don't actually display them at this point because I send all the output to dev null. I just check to see if there are any, and if there are, then I display them. Again, there's that call to heading, and now this time I'm calling print records again, but the input that I send to print records is the output from the grep program. So I'm going to grep, search for that string that they typed in, send that, and send all that information to print records, and of course pipe all of that to more. Now I'm actually creating an exit status for this function here. Don't forget this is the do search function, and do search function is actually going to have an exit status which is going to be essentially the same as grep's. So we'll return 0 if we found some records, or we'll return 1 if we don't find any records, and that will help us with the do delete function, which is just coming up. So this little else here is the else from this if statement, so that'll be essentially saying if grep did not find any of those records in the file, then we'll just simply say sorry, there are none. And then we get down to the do delete, which will do the following. The very first thing it will do is we'll call the do search function, so it'll do all of that. In other words, it'll prompt the user to enter a string, and it'll display all the records that match that string. And then, if that succeeds, in other words, if I did manage to find some, it will do a yes, no, do you want to delete all these records? And if they say no to that, then we'll just simply return from this function because there's nothing more to do. So if we continue on, that'll be because they said yes to the yes, no question. So now we just go ahead and delete the records. Now if this is a special case, I guess, that if they just pressed enter when they were asked for that particular pattern, in other words the string that they entered is empty, then just clear the file, because they've asked essentially to delete all the records, so we'll just start again with an empty file rather than doing any of the other complex processing down below. So we can say all the records have been deleted, and then otherwise if they did enter a string, then we need to use sed, and here is the use of sed. Now, so here we're going to be saying search for all the lines in the file that match the given string and delete them. and the results of that are going to go to our temp file, and that's our temp file from right up at the beginning of the program, and then we'll simply move the temp file back to the original file name. So that's why we needed a temp file, and all the records containing the text blah 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 have been deleted. And moving along, here are our trap lines. If the user types in Control-C or Control/, then we'll call the quit function, which will say, do you really wish to quit now? And if we get a signal hang up or a terminating signal, then we will just exit the program straight away with an exit status of 0. And that's pretty much it. I think there weren't many other changes other than the fact that in the loop, in the main loop, we now can just simply call the quit function rather than here putting the yes/no function, do you really wish to quit? We can just call the quit function. And that's about it. So let's test it and see if it works. Okay, so here's the program running. Now what I'll do is the very first thing I'll test is to see whether that trap function is working properly. So I'll type in Control-C now. Okay, so I'm hitting Control-C on the keyboard, and I get, do you really wish to exit? Yes or no? Well, that's good. And if I say no, then, well, nothing's happened, and that's the right thing that's supposed to happen. I'm back again waiting for another answer. So I could try it again, Control-C, do you really wish to exit? And this time I say yes, and I have exited with a status of 3. So I'm back in again now. The trap facility is clearly working. Now I've created some records, and those are the 3 little simple test records in the database. And what I'll do is I will search for ones that have a B in them, and that was working. And notice they are being displayed in exactly the same way as they were being displayed before. So now I'll test out option number 4 to delete records. So 4, enter the pattern to search for. How about C this time? Delete all these records, and I'll say yes. All records containing text C deleted. Okay, let's see if that's actually true. We'll view the records, and only A and B remain. Okay, so that seems to be working. So as you can see now, we've got a program that has got no duplicated code. Everything has been put into functions. All 4 menu options are working. The program will gracefully handle any interrupts that it receives, or at least any common interrupts that it will receive. And it is a rudimentary and simplistic database, but it is actually a working database, which hopefully demonstrates all of the techniques that you would use in a typical shell script. So that completes the course. There is one final movie coming up, just the summary and completion movie. Well, you've made it to the end of the course. Congratulations. As you can see, we now have a full working database shell script that we've been creating incrementally during the entire course. The fully commented program is now nearly 500 lines long. If I'd shown you that shell script at the beginning of the course, or even perhaps halfway through, you would have been considerably daunted, I'm guessing, by the complexity of some of the things you found in the script. Hopefully I have now explained to you every line in that script, and so you would be familiar with the techniques that I've used. I would hazard a guess that those techniques that we've covered in this course so far are going to be sufficient for you for probably, I'd say, 98% of the things that you'd ever need to do in a shell script. So again, congratulations on making it this far. Now, if you'd like to give any feedback or comments about this course, or if you have any questions about shell scripting, I'm more than happy to hear from you. My email address has been included both in the links file that I've included on the CD and also in the author movie, but I'll give it to you again now. My email address is mvirtue, that's MVIRTUE, at zip, that's zip.com.au. Please drop me a line and tell me what you thought about the course. I'd love to hear from you. I promise to answer every single email that I receive. So, thank you.